Hello viewers, welcome to video number 88 of the channel MALACHEMPHILIC, and video number 88 is the 29th episode of Chemical Thermodynamics. Topic of this episode is Carnot cycle, derivation of efficiency of the heat engine. So let's start. In my previous video, I have discussed this heat engine, then parts of this Carnot cycle, efficiency of the heat engine. Link is given in the description box. Then just to make a very quick recapitulation of this previous video. What is this heat engine? Heat engine is the machine that can convert heat into mechanical work. So that is heat engine. Now, according to second law of thermodynamics, heat cannot be completely converted to mechanical work. So, no heat engine can convert 100% of the absorbed heat to the mechanical work. A part of it is converted to mechanical work and the remaining part brings some changes elsewhere, either in the system or surroundings. All these things I have discussed. So, there comes one term that is called efficiency. How much efficient is the heat engine? That means if the heat engine is more efficient, it can convert more percentage of the absorbed heat to the mechanical work. If it is less efficient, it will convert less percentage of the absorbed heat to the mechanical work. So, efficiency term is related to the heat engine. Now, what is efficiency? Efficiency is the fraction of the total amount of heat absorbed by the heat engine and that is converted to mechanical work. That is the efficiency. So, fraction of the amount of heat that is converted to mechanical work, not the complete heat converted to mechanical work. So, the formula of efficiency, that is the work done divided by total heat absorbed. That is the efficiency. That we will discuss in today's video also. Now, Carnot cycle. Here, the extent to which work can be obtained from the heat, that is using heat engine, and its dependence on the temperature of the source and sink is given by Carnot cycle. To what extent the heat can be converted to mechanical work by a heat engine and its dependence on the temperature of two heat reservoirs, that is given in Carnot cycle. In my previous video, I already explained that this Carnot heat engine, it is consisting of one cylinder fitted with an ideal piston, means frictionless and weightless, though practically that is not possible. And the cylinder contains the working substance, which is the 1 mole of an ideal gas, that is the working substance. And this heat engine, this Carnot heat engine, it operates reversibly between the two heat reservoirs. One is at high temperature T2 and which is acting as the source. That means from that reservoir, heat engine absorbs the heat. And other reservoir is at lower temperature T1, which is acting as the sink. That means the residual heat is released to that reservoir during the process by the heat engine. Now, in a complete Carnot cycle is a cyclic process, right? In a complete cycle, this heat engine absorbs some quantity of heat, say that is Q2, from the high temperature heat reservoir or source and convert a part of it to the mechanical work, say W, and the rest of the heat, say Q1, is transferred to the low temperature heat reservoir, that is called the sink. Now, entire Carnot cycle involves 4 steps. And remember, all the steps are reversible. Though practically reversible steps cannot be carried out, but theoretically here we are considering all the steps are reversible. That is in Carnot cycle. The reason I will tell later. Now, what are the 4 steps? First step, isothermal reversible expansion of the ideal gas. Second step, adiabatic reversible expansion of the ideal gas. Third step, isothermal reversible compression of the ideal gas. And fourth step, adiabatic reversible compression. So, now let's see all the steps. Coming to step 1. Okay. Step 1 is isothermal reversible expansion of ideal gas. Now, entire cyclic process, if we represent in the pressure volume curve, that is known as the indicator diagram, then it is like this. This is curve AB. This indicates the first step, that is isothermal reversible expansion of ideal gas. So, the first step is represented by the curve AB. Second step is represented by the curve BC. Third step by CD and fourth step by DA. Right? Now, let's see the first step, which is isothermal reversible expansion. So, here the heat engine, already I told you in the last video that Carnot heat engine is a cylinder. Okay? And this wall of the cylinder, this wall, these are insulated. It is attached with a piston, ideal piston, that is also insulated. But the base is conducting, base is not insulated. Right? And inside the cylinder, 1 mole of an ideal gas is taken. Now, in the first step, this cylinder is kept in contact with the high temperature heat reservoir whose temperature is T2. So, the heat engine absorbs a Q2 amount of heat from the high temperature heat reservoir at temperature T2, and then the gas undergoes isothermal reversible expansion at that constant temperature T2. Isothermal means temperature remains constant, whereby the volume increases from V1 to V2. Right? Then, it is expansion, that means work is done by the gas. Then what will be the work done in this case? We know that isothermal reversible expansion. Isothermal means temperature constant. So, change in internal energy during this process, delta E will be is equal to 0. And we know that from the first law of thermodynamics, Q is equal to delta E plus of this pressure volume work. Pressure volume work done by the gas in case of expansion. So, here sign will be negative. Now, when delta E is equal to 0, then this work done, that will be is equal to your heat absorbed. That we know. And this expression of work done in isothermal reversible expansion, already I derived in my earlier videos, that is equal to, here it is minus W1. W1 represents the work done in the step 1. Minus means it is expansion, work is done by the gas. So, that will be is equal to nRT. N means number of moles. That is equal to 1. So, R, what is the temperature? T2, ln, final volume by initial volume. Final volume V2 divided by initial volume. So, V2 by V1. This is the expression of work done by the gas during this isothermal reversible expansion. It is minus W1. And already I have shown that in isothermal process, work done is equal to heat absorbed during expansion. So therefore, here we can write it has absorbed Q2 amount of heat. So the expression of Q2 also will be is equal to R T2 ln V2 by V1, because delta E is equal to 0. So therefore, and this Q2 is positive sign because heat is absorbed here. So therefore, work done during expansion and heat absorbed both have the same expression in this first step. So, and this is the expression, that is RT ln V2 by V1. Now coming to the second step. What is second step? BC, represented by BC, that is adiabatic reversible expansion of the ideal gas. Now adiabatic means system must be kept insulated. Then what has to be done? The cylinder of the gas must kept in contact with the insulation stand. See, already I told you, in the cylinder walls are insulated. Piston is insulated. Only the base part is conducting. Now the base part is kept in contact with the insulation stand. So entire system will become insulated. Under this condition, the ideal gas undergoes adiabatic reversible expansion, whereby the volume increases from V2 to V3, and during expansion, adiabatic expansion, already you know that adiabatic process means no heat is absorbed during expansion. So work is done at the lieu of the internal energy of the system. So internal energy decreases, therefore temperature decreases. So here the temperature decreases from T2 to T1. Okay. Now adiabatic process means we know that Q is equal to 0, right? And we know Q is equal to, already just now we have written, Q is equal to delta E plus of W. Here it is expansion, so I am putting the sign W. Okay. So as Q is equal to 0, so this W, work done, that will be is equal to, here it is 0, therefore Q is equal to 0, therefore this W, the work done by the gas, by the system, that will be is equal to minus change in internal energy, right? And we know that this dou E by dou T at constant volume is equal to CV, heat capacity at constant volume. So therefore what we can write, that is D is equal to CV dt, right? So if D is equal to CV dt, then what we can write for minus W, say here I am putting is W2. Why W2? Because second step, 2 indicates the second step, that's all. So what will happen? So therefore from here I can write that minus W2, that will be is equal to minus delta E, means minus CV dt. dt means change in the temperature, that is final temperature minus initial temperature. So this I can write minus CV T1 final temperature minus T2, right? So once again I can write minus W2, that will be is equal to, I can write it as CV, that is T2 minus T1. So this is the expression of work done in the second step, which is adiabatic reversible expansion. Now coming to step 3. Step 3 is this step, that is isothermal reversible compression, which is denoted by the curve CD. So isothermal means you have to remove the insulation, because isothermal process means heat exchange will occur. So the insulation is removed and the gas undergoes isothermal reversible compression. Compression means work done on the system. And during compression, it releases Q1 amount of heat to the low temperature heat reservoir, that is called sink, whose temperature is T1. Right? So, this operation is done at the constant temperature T1. Right? It releases Q1 amount of heat to the low temperature sink, whose temperature is T1. And the volume changes from V3 to V4. So, once again, it is the isothermal reversible process. So, therefore, this work done, what will be the expression of work done? Here, work is done on the system. So, sign will be positive. So, I am writing plus W3. That will be equal to R. Here, constant temperature is T1. Then, ln final volume V4 by initial volume, that is V3. Now, in this compression process, heat is released to the sink. So, what is the amount of heat released? Say it is Q1. And heat is released, so it is minus Q1. So, as it is released, so sign is negative, and that expression will be same as that of the work done on the system. That means that is equal to RT1 ln V4 by V3. So this is the expression of work done and heat released during the step 3, that is isothermal reversible compression. Okay. Now coming to the last step, that is step 4. What is step 4? Adiabatic reversible compression, which is denoted by the curve dA. Now adiabatic means once again you have to keep the cylinder on the insulation stand. That means the system is kept insulated and it is subjected to adiabatic reversible compression, whereby its volume will decrease from V4 to V1, and temperature during adiabatic compression, temperature will increase, and the temperature will increase from T1 to T2. So once again it is adiabatic process. So heat exchange, that is Q is equal to 0. So once again I can write it as Q is equal to 0 is equal to change in the internal energy plus this pressure volume work. Here it is done on the system. So plus W4. Right? So here I can write plus W4, that will be is equal to minus delta E, and minus delta E once again I can write it as minus CV dt. dt in the sense, okay, right, dt, that is equal to minus CV, dt means change in temperature, final minus initial, that is T2 minus T1. So this is the expression of work done. It is on the system in the 4th step, that is adiabatic reversible compression. So now what is the net work done by the heat engine? 2 steps work is done by the system, other 2 steps work is done on the system. So therefore the net work done by the system or by the heat engine. Okay, what will be that one? W net, that will be is equal to minus W1, that is in the step 1, then plus of minus W2, that is in the step 2, then step 3, that is plus W3, then step 4, that is plus W4. Now put the expression. What was minus W1? R T2 ln V2 by V1, right? And what was our this minus W2? That means in the step 2 that was, we remember that minus CV, that is not minus CV, it will be T minus CV, T1 minus T2. We have taken plus CV, T2 minus T1. Okay, just now we have derived. Next one is, that is your isothermal reversible compression, that is W3. Work is done on the system. That expression is R T1 ln RT1 ln then V4 by V3. And the last one was, that is W4, that is minus CV T2 minus T1. Already you have derived all this work done in all the 4 steps. So what will happen? This and this will get cancelled. So W net, now it will be is equal to R T2 ln V2 by V1 plus R T1 ln V4 by V3. This is the net work done. Now, next thing is that what is the net heat absorbed? Net heat absorbed means you have seen in the first step heat is absorbed, that is Q2. Third step heat is released, that is Q1. So, net heat absorbed, that will be equal to first step plus Q2 and then plus of minus Q1. So, that is equal to, first step it was RT2 ln V2 by V1 and then minus Q1 was plus RT1 ln V4 by V3. So, what is the conclusion? Conclusion is W net, net work done is equal to net heat absorbed, not the total heat absorbed. Overall heat absorbed was Q2, not Q2. It is the Q2 minus Q1, net heat absorbed. Okay. Now, what we will be doing? This V4 and V3 will take in terms of V2 and V1, right? So, once again, we will write this equation, that is W net is equal to R T2 ln V2 by V1 plus R T1 ln V4 by V3. Okay. Now, once again we will draw this PV curve. We have seen this one. So, here it is T2 V1, then here it is T2 V2, here it is T1 V3 and here it is T1 V4. That was the things, right? Now this step, this A, this is B, this is C and this is D. Now this step BC and DA, these are adiabatic process. Okay. Now we know that for adiabatic process, expansion or contraction, we know that TV to the power gamma minus 1 is constant. So applying this in step 2 and step 4. Okay. Then what it will be? in step 2, see here, T2 V2 to the power gamma minus 1 is equal to T1 V3 to the power gamma minus 1. So, from here, gamma Cp by Cv. From here, we can write T2 by T1, that is equal to V3 by V2 to the power gamma minus 1. This is for step 2. Okay. This one for step 2. Now for step 4, what we can write? The step 4, you see this part. Okay. So T1 V4 to the power gamma minus 1 is equal to T2 V1 to the power gamma minus 1. So what is T2 by T1? T2 by T1 is V4 by V1 to the power gamma minus 1. So this is for your step 4. Right? Now, then what we can write? This is also T2 by T1. This is also T2 by T1. Therefore, what we can write? We can write V3 by V2. Here I am writing. Therefore, here you see V3 by V2. V3 by V2 is equal to V4 by V1. Okay. So V4 by V3 will be equal to then V4 by V3, that will be equal to V1 by V2. So in place of V4 by V3, I can write V1 by V2. So once again, W net is equal to RT2, here it is RT2, RT2 ln V2 by V1 plus RT1 ln V4 by V3. So W net, now I can write W net, that is equal to RT2 ln V2 by V1 plus RT1 ln V1 by V2. So we can write W net is equal to RT2 ln V2 by V1 minus RT1 ln V2 by V1. Right? So here if I take R and ln V2 by V1 as common, then it is T2 minus T1. So this is W net. Now what is the what is the total heat absorbed? That is Q2 plus Q2. That was also, we have already derived. That is RT2 ln V2 by V1. Then efficiency. Eta will be equal to, that is the W net divided by total heat absorbed. Okay, that is the fraction of the heat absorbed that is converted to mechanical work. Not the complete heat can be converted to mechanical work. So this W net is R ln V2 by V1 into T2 minus T1 divided by, what is Q2? R ln V2 by V1 and then T2. So this part get cancelled. So efficiency eta is equal to T2 minus T1 divided by T2, or we can write it as 1 minus T1 by T2. This is the expression of the efficiency of the Carnot heat engine. And you see, this efficiency depends only on the source and sink temperature, not on the nature of the working substance, that is nature of the gas here. All this discussion, that means what all conclusion we can draw from this formula, that I will discuss in my next video. So hope you have understood. Thank you.